Hi, Celeste. Today's talk is going to go over a question I had from Europa14. I don't know the person's name, but it says here, I'm confused as to why you say that a star like our sun is only 100 million years old. Does the shrinking really happen so quick? And my second question is, how does a cool brown dwarf or Jupiter stage star lose matter at all when it's not close to a host star? I would think that being close to another star is a requirement for the evolution of gas giants into ocean worlds of Earth, or the process would take much longer if the star was too cool. Of course. But there's an assumption there that I want to clarify. The sun is very young. The reason why I have it young is because its DH ratios are 1 part per like 10 million. So 1 part deuterium versus 10 million parts hydrogen, and deuterium is the heavier isotope of hydrogen. So you have that mass fractionation that happens over the star's lifetime. Mass fractionation means you have two materials of different densities, and maybe you put them in a centrifuge, like when you sort out blood from plasma, or when you sort out red blood cells from the plasma, from the platelets and whatnot. You put it in a centrifuge and the heavier material sinks to the bottom or to the outside of the centrifuge, and the lighter stuff remains at the top. Similarly with deuterium and hydrogen. The sun hasn't had enough time to sort out the deuterium and the hydrogen. As well, it still has a lot of the hydrogen there, which is the single proton, single electron isotope. And the deuterium is the two centerpieces, the proton and the neutron, and then you have the electron on the outer side. But yeah, plus I think the Russians and the English back in the 1970s, they discovered that the sun is a giant homogeneous ball of plasma. So it's a very young star. I had done a previous calculation where I had the sun as being around 3 million years old. Between 3 and 150 million years old is what I have the sun as being. Of course, I could be wrong, but without a doubt, the sun is very young, because we know what old stars look like. We know what stars look like that are very, very, very old, like the Earth, and even dead stars like Venus and Mercury, which are basically fossilized remains. To answer the second question, how does a cool brown dwarf or a Jupiter stage star lose matter at all when it's not close to a host star? It loses matter very slowly. As well, the assumption there is that Jupiter has always been in the orbit that it's in right now, which is, according to this theory, impossible because it's around 700 million years old and the sun is between 3 and 100 million years old. So how could an object that's older than the sun be orbiting it? That doesn't make any sense, clearly. But that's the assumption astronomers are constantly trying to push upon the public, that all the objects in the solar system are all the same age. They're not all the same age. Jupiter is about 700 million years old. Saturn is about 550 million years old. Neptune and Uranus are between 1.2 and 1.1 billion years old. Earth is around 4.5 billion years old. Venus between 450 and 700 billion years old. Venus is extremely old. And then Mercury, I have Mercury between 7 and 32.75 trillion years old. Mercury is very, 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 very old. It's a fossilized star. It's basically so dead and decrepit and just completely solidified that it just defies our imagination and age. That's the assumption that astronomers have, that all the objects in the solar system are all the same age. So when you have that assumption, Jupiter has always been in its orbit, will never leave its orbit, is somehow emotionally and physically attached to the sun. But that's not true, because the sun's going to shrink, lose its mass, and transition to a red dwarf stage where it doesn't have as strong a gravitational field. So when you have the sun transitioning to a red dwarf, what's going to happen is Jupiter is going to take up more of the barycenter, meaning the center of gravity between the sun and Jupiter, is going to change, which means instead of Jupiter going around in a circle, the sun is going to be dragged with Jupiter a lot easier, and it's going to be more of a double ellipse. And with that being said, the objects that do have a lot less mass are going to be thrown into chaos, and the solar system is going to be rearranged again. Some objects are going to be tossed out of the solar system. Some are going to take up orbit closer to the sun. Some objects are going to move further away from the sun. It's going to happen again, not in our lifetimes, but it does happen over the scales of hundreds of millions of years. And we know this because, well, to answer your question, of course, when you can rearrange the orbits, you can have a Jupiter-sized object being moved a lot closer to the sun. And we have direct observational evidence of this. They're called hot Jupiters, the exoplanets which are evolved stars, which orbit much closer to their hosts. Sorry, I keep on coughing, getting over a cold. But basically, I have a little diagram here. You have Jupiter, a Jupiter-sized object orbiting really close to the sun. And it's going to lose its atmosphere a lot easier. So the end result, if a Jupiter-sized object gets tugged in by a hotter, younger host star like the sun, it's going to be ripped apart a lot quicker, a lot easier. And the remains of that object will be a small moon with no iron core. It's just a dead rock that won't host life at all. Of course, I have that on the diagram here. When you have these are phase curves, but then the transformation curves is like the red line down the center. So you don't see a lot of transformation curves, but basically, if a Jupiter-sized object were to orbit really close to a hotter host, what will happen is the object will go whew, and just slam down here, and it will become a small moon or just a large asteroid a lot quicker. Now, notice this is time. So as time goes on, if it orbits too close, it'll be ripped apart a lot quicker, and it will leave a leftover moon. And that's how basically the majority of the moons are formed, is you have a hot Jupiter that needs that amount of time to form the planet in its interior, but it's ripped apart before it can form a large enough object in the center, resembling what the Earth is. So basically what we're standing on is direct evidence for a gas giant always kind of keeping away from a hotter host enough to form its core without its atmosphere being ripped away too fast. The moons that have had their atmospheres ripped away too fast, well, they were much larger gas giants that had been trapped in a much tighter orbit around a hotter host, and that hotter host just ripped them apart, ripped them to shreds. But as well, that isn't to say it's always going to remain like that, because you have to look at the history or the actual compositions and the layers and differentiation of an object to determine its history. And that's where it gets really, really complex. That's where it's going to need a lot more work on my part. But anyways, to continue with that diagram, if you have Jupiter on a very far orbit, the rate of mass loss will be a lot less. But that's a good thing, because it can form its interior. It can form the planet in its interior, the Earth-like object in its interior, because it has more time to do so. So basically, look at it like a pearl and an oyster. Say you have a rogue particle enter into an oyster, and the oyster wants to protect itself, so it secretes some type of fluid, which then solidifies onto that particle to make it to where it doesn't, disturb the inside of the oyster. And the bigger the pearl you get, the more time that oyster has had to layer material onto that pearl. If you open up the oyster too early, then the pearl isn't going to be very big. As well, if you let the pearl just grow and grow and grow and grow over many, many years, I don't know how long it takes a pearl to grow, that pearl will be very large and be worth a lot of money. Same thing with a planet. If you take a Jupiter-sized object and you place it close to a hotter host, really, really close, it will rip it apart, but kind of in the reverse fashion. you have to look at the pearl analogy as being the very central regions. If that hot Jupiter doesn't have enough material to form that core, then it's going to be a very, very, very small object. But if you take the hot Jupiter and you place it further away, or if it's caught by a hotter host and it's orbiting just far enough away, then you can have a planet formed inside of its interior. Which is kind of funny because astronomers still, to date, they believe that planets are formed in giant disks, yet the process of planet formation happens internal to the star. And when you look at planets and exoplanets and stars, you're looking at various stages of this process. That's why Baz and I designed this diagram here. You know, when you have the dead rocky worlds like Venus and Mercury, they're way the hell down here. Then you have your ocean worlds up here, and you have your gas giants, and then you have your much hotter objects, which are so freakishly hot that they have visible spectrums. And to address the mass loss, remember, hot stars like the sun have a lot of hydrogen and helium. They're mostly hydrogen and helium, the two lightest elements in the universe, the two lightest ones. Meaning, when you heat them up, their average kinetic energy, average kinetic energy is going to be the same per the temperature, but the average velocity is what I meant. The average velocity of those objects is going to be a lot higher than heavier elements such as oxygen, nitrogen, iron, and nickel, and all the way down. I remember I drew a little paper here. This paper dated November 3rd, 2018. Let's see, elemental mass equilibrium and stellar metamorphosis. So, so you have the mass percentage on the y-axis, and this is a very young star, this single line right here. You have it mostly being hydrogen gas, helium and hydrogen gas, but as the star ages and ages, it loses that hydrogen helium gas, and it reaches the point, and this little line right here is iron and nickel. So eventually, the hydrogen helium gas dissipate, and the iron and nickel collect and take up a larger percentage of the mass of the star. Eventually, it reaches an equilibrium point to where the amount of hydrogen matches the amount of iron in the star. And then, when the hydrogen is continually lost past ocean world stages, the iron continues to be collected in the center of the star, forming the iron-nickel core, and a much larger mass percentage is iron versus hydrogen. And that's that. Of course, there's a lot more work to do on that. And to really stress the importance of this idea. The composition of the sun, I don't know if everybody knows this, but the abundance percentage of total mass for the sun is 71% hydrogen, 27.1% helium, and 0.97 oxygen. So basically, like 99% of the mass of the sun is just hydrogen, helium, and oxygen. And then you have carbon, nitrogen, and silicon on there, and magnesium, neon, iron, and sulfur. And you have a bunch of other trace gases. About 67 elements have been detected in the solar spectrum, but I guarantee you all elements are in the sun. And what's really cool, and this kind of appeases like the 12-year-old me when I was interested in rocks and minerals and stuff. When you have young stars, you know, you think, well, the astronomers, they know what they're talking about. The geologists, they know what they're talking about. They know how all this works. You know, they're infallible with their perfect mathematical theories and stuff. But unfortunately, when it comes to planet formation and star evolution, they're heavily misguided. And one of the reasons why I know they're heavily misguided is basically the rocks and minerals themselves. Rocks and minerals don't form in the vacuum of outer space. You need something to mix those elements together chemically and under extreme temperatures and pressures. And to mix them chemically and under extreme temperatures and pressures in various forms, it takes a star, many hundreds of millions of years to do that. And we're looking at the remains of the core of an ancient star that's been so highly evolved in fact, that the elements have been able to make very unique chemical crystalline combinations. For instance, see 1, 2, 3, 4, 5, 6. The sixth most abundant element by mass on the sun is silicon. And the third most abundant is oxygen. What do oxygen and silicon make? They make silicon dioxide. And I have a piece of silicon dioxide here. It's a quartz crystal. Now, it's kind of unreal thinking that, something like this is basically a star crystal. But it's here, it's real. The sand on the beach is a bunch of star crystals. The water, the atmosphere you breathe is the atmosphere of a very, very, very old star. But I think it's going to take a lot more time for astronomers to realize what's going on. I was going to talk a little bit more about mean velocity, but essentially, it's going to take them a lot more time to realize what's going on, because one thing I've learned about learning new ideas is you have to kind of get rid of the old ideas, the ideas that sort of get in the way of you learning something new. It's like that part in the movie Avatar where the female native was like, you can't be taught because, your glass is already full. You can't fill a cup which is already full. And I was very fortunate, like the guy in the movie, I'm a jarhead. My cup was very, very empty. I didn't have anything in there to start with. A lot of astronomers now, when they look at the stars, they already believe they know how they work. So naturally, they're not going to actually understand what they're talking about because they already have a preconception as to what they consider to be valid information. So in that case, you can't fill a cup which is already full. Which is why it's going to take a long time for astronomers to understand that planets are ancient stars. They were never mutually exclusive. And hopefully these talks helps at least somebody. All right, you guys. Today is December 7th, 2019. Later.